Hello and welcome to our webinar, Understanding Your AC Interference Mitigation Options. I'm Anna Wilson, Corporate Marketing Manager at American Innovations, and I'm here with Andy Florence, our Director of Pipeline Integrity Management Services, and Clay Brailsford, President of Bass Engineering. Please submit any questions you have during the webinar at any time, and we'll answer them at the end. And don't worry, if we don't get to your question, we'll reply to you by email. So without further ado, I'll hand this over to Andy.
Hold on just a second. Here we go. There we go. So there's your pretty face, Clay, Andy, Anna. I had a little problem with the clicker there. Anna, thank you. Thank you for handing over the presentation and the introductions. As she talked about, I'll be your panelist today. Clay will be doing most of your presentations. For those of you who have joined us last 2 weeks ago, part one of our sessions, we took an hour out of your day to explain to you exactly what AC interference is. We gave you a definition of AC interference. We set the stage at a high level. Is this really a problem that you can expect to see in the field? With some of the macro factors that we looked at: urbanization, co-location, cost of land, growing infrastructure. We came to the conclusion that indeed AC interference, if you haven't seen the problem yet, you will see it eventually. We then went on to define the problem, gave you three distinct types of AC interference, or three types of mechanisms for AC interference. Told you what to look for in the field when you've got the ditch open and you're looking at your pipeline. What are the characteristics of AC interference to let you know that you have a problem? We used an analogy at that time that AC interference characterized it as a multi-headed monster. It's elusive, it's dynamic, it's really hard to pin down. And we came to the conclusion that you'll never kill this monster. What you're going to have to do is tame this monster. You're going to have to put a leash on it, a short leash on it, and control it. And that's really what we're going to be talking about today. Now that you understand that you have an AC interference problem, you know what you're looking for out in the field, what can you do to tame this monster? We're going to talk about mitigation options. How do you get this thing under control? So we appreciate you taking an hour out of your day. It's a busy time in the oil and gas industry, a great time in the pipeline industry in particular. I know you're all very busy, so for you to take an hour out of your day and spend it with us, we're very grateful for that. With that, I'm going to hand it over to Clay. He's the primary speaker today, and we'll be talking about your mitigation options, and then we'll circle back and tell you what's coming up next after that. So Clay, if you don't mind, enlighten our audience, please.
Great, thanks, Andy. So just bringing you back to where we were. Bear with us here just a minute. We use the definition of AC interference as taken from the INGA report. And so this is just a reminder of where we left off. And so, of course, we're talking about co-located facilities. And when we co-locate those facilities, we can have a complex electromagnetic interaction. So again, just as a reminder, we identified the three methods of coupling that energy: capacitive coupling, that takes place during pipeline construction. That's a constant threat to personnel, both your pipeline installation folks, your inspectors, anyone, even the general public that may be around that pipeline during that time. Our second method of coupling we identified as inductive. So once the pipeline's in operation, so it's mostly buried with some above ground appurtenances, we're going to see those inductive effects. Again, that's a constant threat, and that's presenting risk to personnel, pipeline equipment, CP systems, and the pipeline itself. And then finally, resistive coupling. Again, while the pipeline's in operation, that's an intermittent threat. It's going to affect those same four areas or same four assets: our personnel, our pipeline equipment, our cathodic protection systems, and our pipeline. Now, we use the asterisks to draw your attention to the primary focus of our mitigation design. So those inductive and resistive coupling effects are what our mitigation systems are designed to address. Our capacitive effects can be taken care of with some temporary grounding during pipeline construction. That doesn't minimize that threat, that simply differentiates it from during pipeline construction and after construction, or what we choose to refer to as in operation. So while many of us can be involved in the design of both electric power generation or the pipeline system itself, many of us find ourselves in the situation that you see on your screen now. Is we're handed a pipeline system to operate, and when you show up, you find out that, well, yes, it is indeed parallel to high voltage AC, and everyone's looking at you to come up with an answer. What do we need to do? So if you find yourself in this position, as so many of us do, probably the next thing that you're going to look at is trying to make a decision between how much work do I need to put into this to come up with an answer. So we've chosen to give you two different approaches here. The one on the right side of your screen, but that we've labeled computer-based modeling. And in blue, we've given you a number of facts that are related to that computer-based modeling. On the far right side, we're contrasting that with an engineered field design, again with somewhat similar pro-con feel to this. Now, what we're not saying is one of these is right and one of these is wrong. That's not the case at all. They're both extremely valuable tools. But as in most things in corrosion control, the answer lies in it depends. So let's first look at computer-based modeling. We're going to need a good bit of field data in order to run those models correctly. We're going to need detailed operating data from the AC system. We're going to need design data from that system as well. In other words, how high are the conductors above the ground? What's the distance from the center line of the pipeline to each one of the three phases that you might see represented? So you can see it's a good bit of detailed data that goes into those models. Interesting to note that if you don't have that data or you cannot obtain that data, most often we have no choice to make an assumption. And as engineers, when faced with making assumptions, we're going to move that slider all the way to the safe end of the scale. So whatever the worst case scenario is, that's the assumption we're going to make. I have no argument with that at all. I think that is the right approach to take. But in many times when we do that, that forces the model to generate a single solution based on worst case scenarios, which may or may not be the actual situation that you're experiencing. Now, I want to contrast that to an engineered field design where, yes, you still need field data. However, we can work with much less AC operating data and AC design data. And then in the solution that's going to come from that, you're going to see multiple mitigation tools employed so that we're not limited to one solution. We're going to use a number of tools to create an integrated solution to this complex electromagnetic interaction. A little bit more about computer-based modeling. If you look through that, you'll find there's a number of complex mathematical equations that we put to work. So again, the level of detail that's required to use these equations effectively is quite daunting. So as you look through each of these, and I'm not going to read each one of them to you, but Carson's equation, Maxwell's electromagnetic field equation, Sommerfeld integrals, Dwight's equation, there's one that you might recognize from your CP work. But all of those rather complex mathematical equations are employed in the computer-based modeling. That can lead to a really, really accurate model of the effects of that high voltage AC on your pipeline system. But remember, if you do not have the proper data to put into the model, you're forced to assume that data. Here's an example of some of the questions that a computer modeler might ask you as an operator that will tend to drive the answer that the computer modeling is going to give you. So for instance, if we're talking about coating stress and we're talking about the pipeline coating, so you'll be asked the question, what is an acceptable coating stress voltage limit? If you know that answer on the top of your head, good for you. If you don't, here are some typical values that you might consider. As you can see, they vary quite a bit. And depending on which one of these that you pick, the solution that will come out of the model will be very, very different. You have to make some allowance for coating thickness. So again, if you know that and it's a uniform thickness up and down your pipeline, good for you. I don't know of many that look like that. Even our new pipelines, we use abrasive resistant overcoats. So we have to take those into account in the computer modeling. You have to understand something about the duration of the AC fault condition that you're considering. Is this going to be a 60 hertz fault or is it going to be lightning? If it is an AC, a 60 hertz event, what is the time length of that event? Is it a single cycle? Is it 3 to 5 cycles, which is where most of our breakers are going to operate on those HVAC systems? Or could it be considered constant? What about our above ground appurtenances? What are we doing to protect our personnel when these events happen? What about pipeline segments that are adjacent to the co-location? So again, if you think about the modeling, if we're only going to look at that area that is co-located, we can sometimes limit the solution, or we're going to force the solution to a predetermined end. And that predetermined end will look like a linear grounding system. So again, not that that's a wrong solution. In many cases, it is perfectly acceptable. However, our linear grounding systems pose a number of installation problems for our operating personnel. And so it's something that we need to think through. So in the end, our computer-based modeling can kind of look like forecasting hurricanes. Nothing wrong with that. It's extremely useful information, but it's highly dependent on the data that we put in on the front end. So as long as we have very accurate data, we can use that model to its full power and come up with very targeted solutions. However, when we don't have that, it's most often going to show up when we specify that coating stress voltage. Other than that, we can have a number of assumptions that we're working through. We may have to run this model many, many times, depending on how many times we change those input variables. Every time we run the model, we drive that cost up a little bit more. It's difficult to model these dynamic events. Remember, in our last session, we talked about how dynamic this AC interference is. It does not stay constant. It changes with load conditions on the power system. So if we're modeling for the highest current rating that could ever be handled on that power system, many times I can drive the solution of the model to a very, very conservative end. Once again, not speaking against computer-based modeling. It is an extremely valuable tool in the right context. Many times it can represent overkill for the situations most of us encounter on a day-to-day basis. Well, let's give some equal time to our engineered field design. So as we look at the right-hand side of that balance beam, I want you to think about going into the field and actually differentiating between above and below ground assets. Because you see, those above ground assets represent locations where personnel can experience touch and step potential changes. We know that we have a set of tools that we can control that with, primarily our gradient control mats. We can also identify electrical isolation locations. Our electrical isolation locations are something that sometimes they're where you expect them to be. Many times they're where you don't expect them to be. Many times they're not where they should be. So all of those things become critical to the engineered field design, because you see, where we find those electrical isolation locations, we have to design specifically for those using decouplers. We can use engineered grounding systems in targeted locations to accomplish the end result that we want, which is essentially moving that energy away from the pipeline, safely moving that energy away from the pipeline. So with some very targeted, very strategic engineered grounding solutions, we can make that happen. We might even be able to incorporate natural grounds. Those would include things like road or railroad casings, any other metallic structures that we can incorporate into the integrated grounding solution. We have to think through lightning and how that event affects both the HVAC system and then the subsequent impact on our pipeline system. Lightning is a different fault condition than an AC 60 hertz event, because you see, lightning does not only present as a 60 hertz event. It has extremely fast rise times. It has a slow decay time or a slower decay time, and it's not a defined frequency. Most often it will have components of very high frequency as a part of that. So the way that you think through that is high frequency does not like long lead lengths. So as you're designing your mitigation system and installing it, you have to be very, very careful to keep all connecting leads extremely short, so that you're not only mitigating for 60 hertz events, but you allow your mitigation system to function under lightning conditions just as effectively. As a part of that field design, you'll be looking at safe arc distances. We want to pay particular attention to those areas where we're close to or adjacent to substations. One of the surprising facts that we find in the field design is observing any guy anchors that may be associated with the HVAC system. So many times those guy anchors are interconnected into the neutral system of the HVAC system. So that means that while your pipeline center line may be 25 or 30 feet away from the nearest tower leg, you may find yourself in close proximity to one of these tower anchors. So those things are best addressed from a field design perspective. As an example, the last point there is incorporating monitoring. We referenced this in our prior presentation, and as we move forward, it's extremely important that you design monitoring into the AC mitigation design, because once again, we're going to stress the dynamic nature of this multi-headed beast. We know it's going to change. We know it's going to morph into some other shape. So the monitoring facilities become critical as we install the mitigation system, that we can constantly monitor this and get a great handle on what's actually happening real time in the field. Here's an example of how we might address an above ground appurtenance. In the photo there on the right, I hope that you can see what that represents is a valve station, a rather common valve station that you might find in the field. This particular valve station was equipped with a chain link fence for security. You can see that the fence fabric has been removed, but you can still see the fence post, the footprint, if you will, around that block valve. But as you design these gradient control mats, understand that we have to extend the gradient control mats outside that footprint, because you see, as you approach that gate, as so many of us do, and you reach down to grab the lock and unlock that gate, you want to know that you're already on that gradient control mat. So the gradient control mat designs become much more targeted, and we're able to incorporate protection for step and step touch potential hazards, and we're going to include that chain link fence, those fence posts, and any other barricades that might be there in that gradient control mat system. Another point that's often overlooked with our gradient control mats is, remember, the gradient control mats will be decoupled for DC purposes from the pipeline itself. So that mat material will not have the benefit of any cathodic protection that's on your pipeline. So we will design a very simple galvanic cathodic protection system that is designed to protect just the mat material in these applications. So in the end, you should end up with an integrated solution when you use this approach. So it's not a single solution, but as you can see, if we trace our idyllic system here from left to right. So in this case, I'm going to start at the bottom left of this particular diagram. And so you can see, as the blue line, which represents our pipeline, as it changes from a vertical to a horizontal position, that represents a change in direction of the pipeline relative to the power line. That might be a good location for a deep vertical point ground. And then you see us entering a block valve, so some kind of above ground appurtenance. Most likely we would consider a gradient control mat there. You see another change as we move from horizontal to vertical again. We might use a coupon test station there to monitor the effects of AC on our pipeline, and more importantly, our AC current density at that location. You see us then crossing the power line, and then we make another change from vertical to horizontal. So another good potential location for a deep vertical point ground. Then at the top center of our diagram, you see a cased crossing with exposed vents, as so many of us are familiar with. We might choose to use that casing as a natural ground. Now, if we do that, we'll be installing small gradient control mats around each of those vents, because you see, once we do that, we're going to make that casing and its attached vents part of the grounding system. So we're going to protect personnel as they approach and are able to touch those vents. Another coupon test station, and then as we change from horizontal to vertical, we go finally to another coupon test station, and then the block valve that you see at the bottom right of our diagram, you see a insulated flange there. So you see us employing a DC decoupling device there to protect the electrical isolation device, and then finally a final coupon test station as we make that last change. So again, what we're trying to convey is this integrated package of solutions that, when properly and strategically aligned, can offer a very complete AC mitigation system for that pipeline asset. So let's look at each one of those tools in a little more detail. Again, we've mentioned several, but I wanted to present them to you in a list. So here you see engineering controls, decoupling devices, engineered grounding systems, gradient control mats, and coupon test stations. We're going to try to use all of those in an integrated approach. Signage is very simple, but it can be very, very effective in helping both our operating personnel and the general public when they're approaching these facilities. So in this case, it's a passive system, but we're just trying to warn folks that AC voltage may be present on those structures. It can be effective for the general public and our operating folks. Another part of our toolkit would be our test stations. So when we're using test stations that we need for both cathodic protection monitoring and our AC mitigation system monitoring, we want to make sure and use dead front connections with all of those. What that allows us to do is safely test our system without making direct contact to the pipeline itself. So if you want a quick analogy for this, this is much like the wall receptacle in the office that you're probably looking at right now. We all know that that's 120 volts AC behind that receptacle. And we know that that's plenty of voltage to cause us great harm, but yet we safely use those each and every day. By the same token, we can safely operate our pipeline systems even though we could have coupled AC energy onto them by simply taking advantage of the tools that are there for us. Decoupling devices. These devices become an integral part of many of our AC mitigation systems. We use them to minimize the threat to personnel, pipeline equipment, and the pipeline itself. Their main function in life is to block DC energy and pass AC energy. Rarely will you see them used alone. Most often they're going to be used in conjunction with other AC mitigation tools. Just a quick history for you of decoupling devices. Some of the earliest decoupling devices that we employed in this industry were zinc grounding cells that you see pictured here. Simply two zinc anodes. They're packaged in a single bag. They each have their own individual leads, and many times those were used across an insulated flange. The idea being that under DC conditions, there was enough resistance in that circuit that the DC current would not flow across that cell. But in the event of a high voltage AC condition, it would easily pass through the zinc anode connection, thus protecting the insulating kit. From there, the industry saw Kirk cells or polarization cells come online. They were used for many number of years, and finally coming up with the polarization cell replacement, or PCR, that many of us see today. And then its little brother, the solid state decoupler, or SSD. So those are the two devices that you see in widespread use today. I want to point out in that top right photograph where you see the polarization cell and you see those brackets that are supporting it, those are fairly substantial brackets. And they're not designed, they are designed to support the weight of the PCR, but they don't need to be that robust to support that PCR. The main reason that you see those very substantial brackets is to pass rated current across that insulating kit. So in this case, I believe that is a 15 Ka or 15,000 amp rated PCR. So those brackets are designed to carry that current, obviously for a very short amount of time, but that's one of those brackets are designed the way they are. Another side note for our decoupling installations, remember we talked about lead length. So in the photo there in the center of the screen, you can see at the red circle, what we're trying to show you is a coupling nut. So that's actually the connection to the pipeline. So it's hard to get much shorter than that. That is a direct connection using pin brazing technology to connect to the pipeline. The other two leads that you see on that SSD actually are redundant leads that connect to the gradient control mat that you can see there in the background. On the far right is simply a photograph of us using pin brazing technology to make those connections to that vertical riser or vertical pipe section. When we talk about engineered grounding systems, there are a number of grounding systems that we might employ. The one that I'm trying to depict here is just a deep vertical point ground. So we want to use these engineered grounding systems to go after threats to personnel, pipeline equipment, our CP systems, and our pipelines. So you can see these engineered grounding systems are designed to address those 4 areas of risk that we've identified. Now remember, our deep vertical point grounds must be decoupled from our pipeline. So you'll be sizing those decoupling devices depending on the location that you're working in. Just a couple of quick photographs to give you some example of what these point grounds might involve. Most often, some type of water well drilling equipment will be utilized to drill a hole, and then we're going to complete that installation with a grounding conductor. Many times it would be a 2-aught multi-strand copper cable filled with a conductive backfill. So we're essentially building a really, really large ground rod. In this particular example, what we're showing you on the far left is the drilling rig apparatus. Rather substantial drilling bit was required in this particular location because of the rock formations that we encountered. And it happened to be done in an urban environment. So while we were drilling with air equipment, we needed to contain the dust. So you see a giant dust bag on the discharge side of the rig. What are some other engineered grounding systems or other engineered grounds that we might use? Well, you can see there on the far left a linear ground, which is exactly what the name implies. It's a grounding system that parallels the pipeline. Again, decoupling that linear ground from the pipeline. On linear grounds, you'll typically see those decouplers installed every 1,000 feet. So understand what that looks like out on the right-of-way is every 1,000 feet, you're going to have an above ground appurtenance where you decouple that linear grounding system from your pipeline. On the far right, what we would refer to as a linear array. In this case, you'll see us use those most often when we're going by a substation, when our pipeline is adjacent to a substation. So in this case, we're combining that linear grounding system with some vertical drilled holes, and we'll augment that linear ground with additional grounds, either using zinc anodes or bare copper, again with conductive backfill, and once again decoupling that array from the pipeline itself. You'll notice that the array is installed between the substation and the pipeline. That's very intentional to augment the current discharge from the pipeline back to the grounding system that's associated with that substation. And then finally, there in the middle, just a simple diagram of what a natural ground to a casing might look like. Again, a connection to the pipeline, a connection to the casing with a decoupler between the two. Gradient control mats are another tool in our toolbox. They're extremely helpful in collapsing those high voltage gradients that can occur during fault events on the HVAC structures, whether those fault events are 60 hertz or lightning. So the step potential that you see represented on the left side of the screen, or the touch potentials that you see represented on the right side of the screen. In both cases, we're indicating an SSD is used to decouple that gradient control mat from the pipeline itself. Some photographs to help you understand how those gradient control mats are assembled in the field. The mats themselves would come to you as a 4-foot by 8-foot structure. The grid pattern should be no larger than 3-inch squares. As you assemble those mats together, there's a seam that's created when you do that. Those seams need to be joined exothermically every 18 inches. Again, you're building a gradient control mat. So it's essential that you electrically connect that mat so that it functions as a monolithic structure. So as we create those exothermic wells, you'll see us come back over the top of that to coat that connection, usually using a wax tape product to do that. And then finally, on the photograph on the bottom right, you see the magnesium anode connection attaching to that gradient control mat. Now, many of you may look at that and say, wow, that's not the typical mag anode lead that I'm used to seeing. And you're correct. We actually upsize that cable. In this case, we're using a number 6 AWG HMWPE lead to connect that anode to the gradient control mat. And the reason we do that is in the event of fault currents, we could expect some current to flow to ground through the mat, and inevitably some of it could flow off of the magnesium anodes. That's not what they're intended for. The mag anodes are only there to protect the mat. However, you should consider that they could see large current flow. Thus, we upsize that cable to accommodate that. And finally, monitoring. We talked about the importance of monitoring earlier in the presentation, and the fact that we're going to have to keep an eye on this beast. Most often, you're going to use some type of coupon test station for that monitoring. In this case, You can see the coupon place, the actual coupon reference cell placement adjacent to the pipe. This particular coupon test station would need to be installed in a vertical position. We recommend no more than 12 inches away from the pipe, and typically at a 5 to 7 o'clock position of the pipeline itself. The backfill that goes around that coupon is extremely important. We would encourage everyone to backfill with native material only. So in other words, if you're using a hydrovac, for instance, and you've got this mix of muddy water, you probably want to make provision for some dry backfill material that's either from a nearby location or is very, very close in composition to what's around the pipeline itself. You'll see us recommend air excavation in most cases. Air excavation allows us to use that reuse that backfill material. So as we excavate that hole, we can simply empty the tank and use that same material to go back around the coupon itself. Again, loose backfill around the coupons is not good. We need to try to approximate the compaction on the coupon that the pipeline is seeing. So most often you'll see us recommend air tamping of that backfill, obviously taking care not to damage the coupon assembly itself. So that's getting us close to the end. We have a review question here for you. So as you look through this question and you consider your options here for answers, which of the following is not a decoupling device? Well, our first example is a Kirk cell. Yes, we mentioned that. The second is a deep state decoupler. I don't remember talking about that one. Number 3, a polarization cell replacement. And number 4, zinc grounding cells. So I think the obvious answer is the deep state decoupler is out. He is not, at least today, identified as a suitable decoupling device. How about number 2? The proper centering distance to exothermically weld your gradient control mats. 1 inch, 12 inches, 18 inches, or it is not important. I hope you remember that we actually want to build those seams with our exothermic welds at 18 inches in order to safely accomplish a monolithic structure when we're through. So in that case, number 3 would be the right answer, 18 inches. So that's bringing us at 10:45, and that's going to leave us a bit of time for some Q&A. So with that, I'm going to see if we've had any questions come in, and if not, we'll see what we can come up with. How about that?
Clay, one question that came up was on these deep vertical ground points. Typically, how far down do you have to drill? And how long does it take you to do it?
Right, that's a great question. Again, you'll see us, we always use the term engineered ground. So once again, the answer is going to be, it depends. So as we build the grounding systems, we're going to gather data about that physical location. So we're going to know something about the soil resistance and its associated resistivity. And then we'll use Dwight's equation, that same equation that we referenced earlier in the presentation, to engineer that grounding system to achieve a low resistant ground in the given environment. Understand, we don't get to pick where we find this co-location. So if that co-location happens to be occurring in South Louisiana, and we have great low resistant soil, our engineered grounding systems are relatively easy to install, to design and install. However, sometimes that co-location can occur in areas where there's a good deal of rock. And many of us understand that rock is a high resistivity medium. And so our grounding has to take a different look when we approach that. So each of these engineered grounds are just that. They're engineered for the specific location that they're going to be installed. Now, to answer your question more directly, usually, typically, you might see these deep vertical point grounds at 200 to 250 feet. Again, that's typical. It's not a set in stone answer, but that's typical for what certainly we've experienced. As far as how long it takes to install those, generally 1 to 2 days is what you should expect for something like that.
Second question, for resistive coupling, or resistive when you have a lightning fault event, obviously the lightning can travel through the wire, through the tower, down to the guy wire, into the ground. What is a recommended safe separation distance from the pipeline to, I guess, the nearest discharge point off the power line?
Well, by now, Andy, you've probably figured out that my answer is it depends. But once again, that safe arc distance is how we refer to that. And the safe arc distance is in large part controlled by two things. The voltage of that strike, and that's what we're trying to determine, or certainly we can calculate. And then secondly, what's the resistance of the soil between the leg of the tower and the pipeline? Because it's a relatively simple electrical circuit. So using Ohm's law, voltage is equal to current times resistance. So with that, we can actually calculate that safe arc distance. So when we say safe arc distance, what we're actually saying is if your pipeline is X feet away from the tower leg, it's safe. It is safe from arcing. So we can determine that for those specific locations once we know the soil resistance and its associated resistivity to help you better understand whether that asset, pipeline asset, is at risk for arcing. If you're inside that arc distance, then that requires mitigation for that particular location.
I don't think we have any more questions. So just on we'll go to the next slide here. So this wraps up part 2 of our 4-part series. Again, part 1, we focused on the definition of AC interference, setting the context of it is a growing problem that you need to be aware of. What is the definition? What do you need to look for? What are the characteristics and symptoms of AC interference in the field? So we gave you an understanding of what AC interference is and how to identify it. Today's topic was we understand AC interference, how do we mitigate it? Going back to the analogy, how do we tame the beast? Put it on a short leash and control it. I think Clay did an excellent job with describing all of the tools in our toolkit that can help us keep our assets safe and keep our people safe as well. Our next topic, part 3, in about 2 weeks, is on AC threat assessment, ACI threat assessment. This is designed for large operators who have a lot of legacy pipe in the ground. Let's suppose you have 7,000 miles of pipe that you've had in the ground for multiple years, and AC interference may not have been top of mind at that point. So now you've got to go back, reassess your network and your pipelines, and identify where the potential for AC interference occurs along my pipeline and go out and do some field assessments and possibly do some mitigation out there. So next week, we're going to talk about how to get a handle on your legacy pipe and understanding the threat to your pipe for AC interference. And then 2 weeks after that, we'll come back and we'll talk about monitoring, one of the more important tools in your toolkit to help you keep tabs on this dynamic and elusive multi-headed monster there.